Okay. Good. Okay, so the reason I set this all up is because, well, we'll go through all of that in detail. Let's see if the Zoom is recording. Okay, great. Okay, how many people do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's a lot of people. Okay, good. So let me shut the door. So welcome everyone to thermodynamics. So this course is Chem 684. What's the official name of this course? Anyone remembers? I always think thermodynamics, but it's got some funny name, right? Like chemical thermodynamics. Okay, that's fine. So we'll go through introductions today for a little bit, just try to familiarize with each other, and then we will gradually get started. So this is graduate thermo, and I'm going to try to get a sense of how much thermo you all have taken and get a sense for things. So it's going to be a relatively abstract course in the sense that there will be a lot of math. You will wake up one fine day and be like, is this chemistry? Is this math? I have no clue. You know, you will feel thought, you will have thoughts like that. Does anyone know here the 3 types of fun? Has anyone heard about the 3 types of fun? You have? You have? No one? Okay. We will get to the 3 types of fun in a little bit. So let's get started. So the first thing I want to do is to start with everyone's introductions. And the way that is going to work is we will go around the room. You should tell me your name. You should tell me your major. You should tell me your year. So this course, last time I taught it, it had people from 5 different majors, including applied math, mechanical engineering, all over the place. It generally has 1 or 2 undergrad. We will see if there is any undergrad. And then I want to know, where were you before this? And then I want to know your favorite math equation. But this is really important. We'll see why. So let's get started.
My name is Mari. I'm a second-year chemistry major. I was in a different class before.
And who's your advisor?
Dr. Block.
Okay.
And
yeah. I don't know anything.
Anything?
Ideal gas law. That's a good one. You're going to do well in this class. Okay. How about you?
My name is Jonathan Stern. I'm a first-year chem grad student. And I guess your math equations, like the rocket equation.
The which one?
The rocket equation.
The rocket equation?
Yeah.
Which one is that?
Just like ISP, specific impulse.
Okay, good. And where were you before this?
I went to school in Massachusetts, actually.
Okay.
Yeah.
Cool. And now, okay, yeah. When I say before this, I also want to know your undergrad major. The reason I ask this is because, this class gets some people with lots of different backgrounds, and it gives me a sense of how to scale the math and things like that. What was your undergrad major?
Oh, chemistry.
Chemistry. And how about you?
Aerospace engineering.
Oh, cool. How about you?
Hi, I'm Steve Douglas. I'm a first-year chemistry PhD student. I got my bachelor's from Boeing University, which is up in South Jersey, in chemistry, and I'm going to go with the
quadratic equation. Okay, cool.
Hi, I'm Jock. I am a 4th-year undergrad chemistry major. So before this, I was in high school, I guess. Favorite math equation: E squared equals m squared c to the 4th plus b squared c squared. That's kind of funny.
And you have a passion for suffering, it seems, right?
I guess so, yeah.
Okay, good.
Let's see if I'm still alive.
We'll see. Okay. How about you? Sure.
major is science in Wisconsin.
Wisconsin medicine. Okay, very good. I went there in January. It was very cold. It doesn't get that cold here. And what's your favorite math equation? Your favorite math equation? Yeah. This is not optional, you have to tell me. No, but which one? You know, like someone said ideal gas law. He said something about E squared, MC squared, 4 squared, something. What's yours?
Maybe the
Which one?
fourth law of thermodynamics.
Fourth law of thermodynamics. Which one is that? First law. Okay, I got worried that there's a fourth one. I like the first law too. Good. This class is going to be a bit opposite. So a lot of you have taken thermodynamics, right? This class, you will be like, I've already taken thermodynamics. What am I doing here? You will see it's a bit different. And this class, we will actually start with the second law. The first law comes later, and you'll see why.
This is Sia, and I went to University of Mary Washington. It's in Fredericksburg, Virginia, and I was a chemistry major. And I'm a first year PhD student in chemistry. Yeah. I guess I like E equals MC squared.
See, this is a collective bias. Now blame you. That's a good one, but there is no relativity in this class. Okay, how about you?
I'm Elizabeth, and I'm a first year in the biophysics PhD program. Before this, I studied just general biology at Bryn Mawr College near Philly. My favorite math equation is Pythagorean theorem.
Oh, that's a good one. I like it a lot. Yeah. Okay.
I'm Anjali. I'm first year in biophysics.
And sorry, I missed that. Yeah.
Okay, yeah, first year of biophysics. Before this, I was just working in a lab, and then I did applied physics in undergrad. It's not an equation, but I like the spherical harmonics, like in quantum, so you can graph them pretty and they like match the orbital shapes.
Okay, very good. How about you?
Oh boy, my name is Matt. I'm a first year chemistry PhD student. Before this, I was at Buffalo State College, and my favorite math equation. Oh man. N equals I sigma x. That's my favorite one.
N is equal to I sigma x. What does that mean?
That is a nuclear reaction equation where you have some target and some beam,
Okay.
and you are solving for based on the intensity and your target thickness and the inherent probability of the reaction. You
Okay.
can solve for
And here, are you planning to work with Leah Dodson?
Dr. Minerick.
Dr. Mehra, yeah. Oh, of course. Alice, right?
Yeah, yeah.
That's awesome. How about you?
Hi, my name is Rohan. I was a physics undergrad and I did my master's in applied physics. My advisor is Michael Hill in the chemical physics. So I'm chemical physics first year student. Before this, I was working at Rochester as an intern, and before that I was at Livermore, and then before that I was at Columbia, and before that I was at the University of Delhi.
Yeah.
And my favorite math equation, I guess, would be Schrodinger's equation.
Good. And you are not doing superconductivity experiments at Rochester, I hope.
No.
You know why I said that, right? Okay. And how about you in the back?
My name is Josh Paul. First year and before I came here, I went around Rochester, and before that, to California, and I moved to health physics too. I'm gonna do really math equations. It's gonna be muscle equation.
Oh, that's a good one.
Just because I like it.
Okay, great.
Hi, my name is Nayeli. I'm a first year in applied physics. I did my undergrad major in chemistry, my master in physics. And so my favorite question is the partition function.
Partition function. Okay. Well, we won't be doing that in this course, but we will get you ready for next semester when you'll be doing a lot of that.
My name is Sanjana and I'm a first year chemistry PhD student. I did not back in India where I majored in chemistry with a minor in physics. My favorite math equation is the slide radius, which is I is equal to G.
Wow, fancy. Okay.
My name is Lydia, and I'm a first year chemistry PhD student as well. And before this, I was in West Virginia at University of Charleston. And I was a chemistry major. And I'm going to say my favorite equation is also E equals MC squared because you put me on the spot and I can't think.
Okay. I hear you. Okay. If it changes, you can send me on Slack. Yeah.
My name is Sarath. I'm also a first year PhD in the chemical physics program. Previously, I was at IISER Pune and I have a master's in chemistry. My favorite equation, well, it's a recent one, which is basically C equal to H cross equal to K equal to 1.
Okay.
My background is only computation chemistry. Favorite math equations, very simple. Put me on the spot, something I can think of now is the convergence series of 1 plus R plus R squared equals to 1 by.
Oh, that's a good one. Yes. Go
My
ahead.
name is Ben. I'm a first year chemistry major. For this, I was here at UMD, also studying chemistry. My favorite math equation, it's the like an Euler identity one.
Mhm. You mean e to the power I pi?
Yeah.
Good. Did you take 481?
Yes, I don't think we thought
I didn't teach it. Lucky you. But okay.
Hi, I'm Kathy. I am a second year PhD student in the geology department. Before this, I was at Franklin Marshall College. That's just in Lancaster, Pennsylvania, and I studied chemistry and geosciences there. My favorite math equation is probably cycle gas law.
And are you here due to free will or because your advisor forced you? Our advisor is my wife. That's okay. Good to know.
Hello, my name is Rashid. I am a second year PhD student of mechanical engineering department. My undergrad was also mechanical engineering, and my favorite equation is Newton's.
Okay, good. And last one in the back.
I'm Shivadev.
No, one more. Yeah.
I'm Shivadev. I'm a first year PhD chemistry student here, and I have done my master's in chemistry from the University of Delhi. And my favorite math equation would be A equals to epsilon CL, where we measure the absorption and transmittance.
Oh, good. Okay, and last person. Okay.
For this, I was at District Polytechnic Institute of Applied Physics. Favorite math equation is the Fourier transform.
That's a good one. Great. So a few of my favorites came up. You had the geometric series. Who had you had the geometric series, right? 1 plus, yeah, that's a good one. The 1 plus r square plus dot 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 equal 1 by 1 minus r. That gets a lot of use in statistical mechanics next semester, not in this one. And apart from ideal gas law, I don't think any of the equations any of you mentioned will be used in this semester. But the course will be very mathy. So, start thinking in terms of math. Some of the math things, we will be doing a lot of partial derivatives in this semester, not so much integration, a lot of differentiation. So things like d by dx of g multiplied by f is equal to f dg by dx plus g df by dx, these type of things. And it just really builds up from here. It should be second nature to you. And it gets much worse as we will go further. The first homework is already out. Have you ever had a professor who gave you homework before the first class?
No.
Yes, good. The first problem is what is known as a Fermi problem. There is no right answer. Enrico Fermi, who was a very, very famous physicist, he used to give problems like that, estimate the number of piano tuners in Chicago. You have to do back of the envelope order of magnitude calculation and get a sense for it. Okay, so don't get, I get the most complicated questions on that one. Like, can I use this number? I don't care what you use. Just think, work through it and think how it is. And apart from that, this first homework is just prerequisites to get you a sense for the type of math you will be doing, and also the results in the first homework are results you will be seeing later. So it's quite useful actually to do it from a purely mathematical perspective, and later on you will be like, aha, this actually makes physical sense. Let me tell you a little bit about myself. So my name is Pratyush Tiwari. My major, I don't know anymore. I did my undergrad in something known as metallurgical engineering, which is the study of metals. Then I did my PhD in material science. So my undergrad was in India. For my PhD, I came to California. And then I did a postdoc in Switzerland. I was living in Switzerland for a couple of years in a city called Lugano, where I moved to chemistry, to theoretical chemistry. And then I was in New York for a couple of years again in chemistry. And here I am in chemistry department. I have joint appointments in many other departments. And I'm physically located in this Institute of Physical Science and Technology, IPST rep, which all the chemical physics and biophysics students probably know. I think it's the crappiest building on campus, but it's got a lot of character. The people inside that building are a lot of fun. And what year am I? I don't know. I got my PhD in 2012 or 2013. So I guess I'm 11th year since PhD. I turned 40 this year, so now I feel ancient. And I told you about my undergrad major. My favorite math equations, I have so many. The one that we are not going to use in this semester is Bayes' theorem, that I like a lot. Who said Pythagoras theorem? Oh yeah, you came close to that, but similar to Pythagoras theorem, I really like the triangle inequality. You know, like A plus B is, anyone remembers the triangle inequality? Is it smaller or larger? Which one is larger? Huh? Right side. What is the practical implication of this inequality? Yeah, anytime you're crossing a football field, go through the diagonal. You know, don't go like this way and that. So it's kind of good. And then I also like e to the power I pi is equal to -1. I think that's a, who said that? That one? You said that one. That's a beautiful equation, right? Three constants just tied together. It's really, really incredible. So, okay, so this is a bit of introduction. I will try to remember everyone's name, but it will take me some time. So far, I just remember Anjali and I remember Maria Delia, right? Yeah. And he is the undergrad, right? You have only one undergrad, right? Yeah, so we can just call you the undergrad. Do you object to that?
I do not.
Okay, we don't have undergrad degeneracy. That's great. So, okay, so let's go over the course syllabus and walk through things. And that's my dog Pakoda. If you're from India, you know Pakoda means appetizer. It's like a fried dumpling. He's quite a bastard. So he looks cute, but he's like, especially he likes to herd all the undergrads and first years. You know, so. Yeah, and let's go to the course website. So I used to have a short form for the website, which UMD had this go.umd.edu thing. They have removed it. So the best, if you get confused, what is the website address? Just go to Google and type Chem684 Tiwari. It comes up. If you go to this one, this is where I will maintain everything. I don't like Elms. It's kind of terrible to post information there. I like to control this. It's in my hands. I can keep everything in a clean manner here. So on this, I will be uploading all the lectures, the homeworks, everything of interest. When COVID happened, you know, or is still going on, but like 3 years ago, everything became virtual, right? All of you must have been through this, right? All the classes became virtual. So that's when I started teaching on Zoom. And then when it came back to real life, I kept the Zoom thing on. So the class is currently being broadcast on Zoom, and we'll talk about that in just a moment. So every class will be recorded, and I will put up a YouTube link like the same day as the class, so you can go back and see things, and if something is not clear. And the notes will also be online, but they will be in my absolutely terrible handwriting. You're going to complain about it very, very loudly for a while, and then you will get accustomed. Because the option to that is that I prepare notes in advance, and I am not going to do that. I have never taught a class using PowerPoint ever in my life, and I want to keep it that way. Okay, I want it to be real. I will make mistakes, and I want you to pinpoint when I make mistakes, you know, so everyone stays engaged. I will be asking questions a lot, so don't fall asleep. Let's go over the syllabus. Am I in junk? Okay. So, okay, so this is fall 2023. You can call me Pratyush, no need to call me professor or anything. And that's the website. There is a textbook, a recommended textbook. It's a book by Callan. Did anyone buy it, find it, PDF it somewhere? Okay, you should. The book is important. If you try to buy it, it's really expensive. It's like $100. So I'm not giving you any suggestions on how to get hold of it, okay? Yeah, no comments. If you keep a hard copy, it's actually really good. You can keep it. If you intend to say in science over the next 10, 15 years, then it's a good investment. If you're like, I gotta get a PhD so I can go work for Boston Constituency Group or something like that, then don't buy it, okay? Then there is a book by Scott Shell, which is recommended. You definitely don't need to buy that one. Callan's book we will be following, and it's an old book. It's an ancient book, but it's kind of remarkable. The examples in that book are really from the 1950s or 60s. So they are clearly women did not do science back then. And, you know, you had, it's kind of funny, some funny and sad examples. You're like, really, who cares for this example? You know? So class format. So I expect people to attend. Now, you don't have to attend in person all the time, okay? If you're not feeling well, if you're just tired, for whatever reason, you woke up late, something happened, it's totally fine, just join on Zoom. I will post the Zoom link on Slack. It's going to be the same link every time. The only condition I have is you have to let me know in advance. Is that fair? If you let me know, and by advance, I mean even 10:55, like, sorry, I just feel like shit today, not gonna come to class. I'm gonna attend on Zoom. That's fine by me, you should do that. However, if you're feeling like shit every week, day after day, then we should talk, right? Then there's something is wrong, then we should have a discussion. So if you're going to a conference or something like that, just join the class on Zoom from there. So, and the same thing applies to me. I travel a lot. I have to go to Germany in 3 weeks, and then I have to go to Switzerland, and I have to go to Chicago, then I have to go to California. I keep traveling, giving talks, all sorts of things. And I don't want some other random substitute teacher to come and teach, right? It just destroys everything. So every once in a while, I will be also teaching on Zoom, and I will let you know well in advance. So this is a policy for your benefit. If you don't want to come to class any particular day, it's totally fine. Just let me know, okay? And it's not like you can do it once or twice. As long as there is a valid reason, it's totally fine. However, you have to let me know in advance. All videos are being recorded on Zoom. They will be put up online. So you can go and watch them if something is not clear. I'm not going to have dedicated office hours because I have done it in the past for this course and the 687 course, and they don't get that well attended. However, what I'm going to do is to have a very, very active Slack channel. So where am I? This one. And if I post jokes here, I expect reactions. You guys, you like not have a soul or something. Like, give me a thumbs up, man. Like this one, first homework is out. You know, what reaction do I expect on this? Of course, I expect party reaction, right? That's the spirit, right? So Slack is going to be very active. After the course starts getting heavy, this works especially for the undergrads, but maybe it will work here also. It does work for grad students too. I set up a channel for Pakoda, especially for my dog, and that will be him comforting you. So photos of him, and it becomes something where other students also start posting their pets photos, and it becomes a whole ensemble of like dogs, rabbits, turtles, goat. One time there was a pet goat. So yeah, but you know, so there won't be dedicated office hours, but you can ask questions here. You can send me a direct message, or you can just ask in general. I will be responding very, very quickly, unless it's the weekend or if it's between 6 p.m. except 6 p.m. and 6 a.m. Between 6 p.m. and 6 a.m. I will be very slow in responding, but starting 6 a.m. normally, I will be very quick in responding. On the weekends, I won't be responding. So just ask me questions here. If it's still not clear, I will set up a meeting, okay? And we will talk in detail. So that's the deal. And this Slack is the free version. So everything will be saved for like 90 days. So, you know, and yeah. And if you have still, is there anyone who has not been able to join Slack yet? Okay, so you need to send me an email, okay? And I will add you. So let's go back to course syllabus. Problem sets and exams. So last time I taught this course, something happened midway the semester which changed the nature of teaching as ChatGPT. right? I used to think that when I went to grad school, every single exam I had was take home, open book, open internet. And now that's become a bit difficult, right? It's a bit hard. There will be, so the way it's going to work is, and I will talk about problem sets and exams together. So there will be 2 midterms and a final exam, okay? The final exam will 100% be in class, okay? That's not going to be take home. The first 2 midterms will most likely be take home. They will be open internet, open chat GPT, whatever you want to do. The final, on the other hand, will be in class, no internet. You will be allowed a cheat sheet. So you can bring an A4 sheet on which you can write whatever you, so you don't have to commit everything to memory, right? There will be these horrible things which we call Maxwell relations. Don't try to commit them to memory. You can just write them on your cheat sheet and things like that, okay? So that's going to be the nature of the exam. And it's very distributed. So your one exam is not going to decide your grade, okay? And the only person who should really be concerned about the grade in this course is the undergrad, okay? No one else. It doesn't matter, you know, if you're above, if you put in a sincere amount of effort, it should be very easy to get an A minus. It will be hard to get an A, it will be really hard to get an A plus. Most students lie around A minus and B plus in this course, okay? However, I have tenure now, so no one can force me to grade on curve or anything like that, you know. So I'm very happy to give everyone A plus if it's truly an A plus performance. I'm also equally happy to give everyone a B minus if it's truly a B minus performance. So, okay, so don't push me to that. And it's very distributed. So first exam is 20%, second is 20%, final is 20%. Homeworks carry 30% of the weight. There will be lots of homework. Your single worst homework will be removed from the grade consideration. Okay, so if you screw up in one homework, it's fine. It doesn't matter. You can make it up. Now, every year there is one smart student who tries to exploit this and does not even submit the last homework. I have other ways of dealing with that, okay? So once we get there. So this does not mean that you simply don't submit one homework. It does not mean that. You try to submit everything. Participation points are 10%. You got 2 points by joining Slack, except you, so you have to join. And apart from that, just ask questions. You know, I'm very happy when someone picks up a mistake in something I wrote. I want to remove my mugshot. Oh yeah, it's gone. So just ask questions. If any, it's when you participate in something, it's obvious that you're participating. You will know it. I will know it. Okay. And midway through the semester, you can ask me, how am I doing in participation? I can tell you, like, who are you? That's not a good sign, right? And this can be participation. Maybe you're shy. Maybe you don't like to interfere in class. I totally get it. In that case, if you are asking me questions on Slack, in general channel, or through direct message, that is also participation. I just want to see that you're involved. And all homework sets and everything you can use, whatever you want, ChatGPT, etc. If I feel that you are not understanding and just copying, because so I use ChatGPT regularly in my coding and things like that. It's obvious the type of mistakes it makes. So if I can see that something is going on, I will call you on the Blackboard and have you solve a problem. And the probability that one of you goes to the Blackboard to solve a problem once in the semester is 1. You will all be coming to the Blackboard at least once, I can promise you. So any questions about any of this before we move to the syllabus? Huh? Say again? Oh, good point. So the homework, yeah, excellent point. So homework you can just write on paper and bring it over here, or you can send it to me on Slack. If you send it to me on Slack, please don't say page number 1 coming, page number 2 coming, you know, make it one PDF and send it to me. It has happened many times. I will, however, print it and grade it. So you're not saving any paper by sending it to me on Slack, because I'm going to print it anyway, because that's how I like to do it. And yeah, and it's due. If it says the due date is Thursday class, it means it's due before the class starts. So when I'm here, you should have got it here. If you need an extension for any valid reason, just let me know in advance. You know, it's totally fine. I'll give you an extension. Good. Any more questions? Yeah, you can do whatever. You're in a PhD class, it's okay. Just don't say, this is so trivial, I'm not going to solve it. No, solve it, because Okay, in derivation, sometimes students pull all sorts of funky things, right? They start from one end, they start from the other end, and they just write a bunch. And it looks like it's a derivation. Clearly, there are some logical steps that take you from here to here, but you haven't written them out, right? So be as detailed as you can. Apart from that, there is no requirement.
If it's a combination of typed and handwritten.
No, not at all. Do whatever. You can calligraph. I don't care. Okay. Anything else? Also, don't worry about grades so much. Okay, it will be easy for you to get a B plus. What did I say? B plus or A minus? Which was it? A minus. Okay, it will be easy. Yeah, somewhere between A minus and B plus, it will be easy. Okay. So the syllabus is up here. It's really 6 parts. So it does not mean that it will be 1/6 of the semester. It will be highly non-linear. We'll start with an introduction of the course, which we will start today. We'll spend a lot of time thinking about entropy and second law of thermodynamics. That's how this course really begins. Who here thinks that they really, no one told me the entropy formula, right? Who thinks they understand entropy? Is anyone bold enough to say that? Good, that's the right answer, because even I don't understand. It's really complicated. We will try to understand it together. Then we will go to energy and first law of thermodynamics. We will take a combined look at first and second laws. And then we will think about these general thermodynamic potential. So this is a lot of math. Even though this is 5-part, this might take not 5/6 of the semester, but something like 50% of the semester. The 6th part, which is applications, will take a lot of part, depending on how we get there. And how many applications we cover, that depends on how our speed is. I'm not going to miss any class due to travel or things like that. Like I said, if I'm traveling, class will be on Zoom, and I will let you know well in advance so you can plan. In applications, we will look at things like phase diagrams, we will look at solutions, how things mix with each other. We will talk about chemical equilibrium, and we will talk a little bit about how to get kinetics from thermodynamics. Okay? And this is going to be classical thermodynamics. There is absolutely zero stat mech, and I will tell you why there is no stat mech in this course and why this sequence is special in Maryland. Any questions about this? Okay. So let's get started actually. And all these notes are going to be available online. The videos will be available online. My handwriting is going to suck. So that's the only reason why you might want to note down something, but otherwise everything is going to be available online. So what are we doing? We are studying basically classical thermodynamics, as opposed to quantum thermodynamics, which is an exciting area which is going on. So classical thermodynamics is an old subject. It really started with a French engineer named Carnot. I think he's supposed to be the father of thermodynamics. It's been there for a while. And it sounds like a very old-fashioned subject, but it's a really, really important subject. In fact, I want to show you a quotation by Einstein, who came up many times today in E is equal to mc square and things like that. But if you asked Einstein himself what he felt about thermodynamics, he said, "It is the only physical theory of universal content which I'm convinced, within the framework of applicability of its basic concepts, will never be overthrown." It's a mouthful, but what it really means is thermodynamics is going to last, right? Relativity came and over, like, kind of generalized classical mechanics, right? And quantum mechanics came and generalized something else. Thermodynamics has kind of stayed. It's not going to change. It's really, really fundamental. So what is it all about? So we will gradually get into the subject matter. Okay, let me just try to motivate it. So it's like all of chemistry, this is the study of matter, right? So when you think about matter, how many atoms do you think any normal sample of matter has? Around? Huh? Avogadro, right? Around 10 to the power 23. What's your name? Sanath?
Sarath.
How do you spell it?
Sarath.
Sarath. So Sarath said that a typical matter, for example, Sarath, who is a typical matter, is made up of 10 to the power 23 number of atoms, right? So If I have to describe Sarath, does it mean that I have to write down x1, x2, x3, x 10 to the power 23, assuming Sarath moves only in one line? Sarath really does not like to move in one line. Sarath lives in a three-dimensional world, right? So Sarath moves in three directions. y1, y2, y3, y10 to power 23, z1, z2. Is this sufficient to describe Sarath? What are we missing? The velocity, the momentum, right? This just says where Sarath is sitting, where every atom is sitting. It does not say whether it is moving in some direction or not, right? So we also need to have the momentum. We need to have, so let me just call it x1 to x to the power 3 into 10 to the power 23, right? X, Y, Z, we just call them as x, and momentum p1, p3 into 10 to the power 23. So how many variables is that in total? 6 into 10 to the power 23, approximately, right? Something like 10 to the power 24 number of variables. So next time Sarath is late to class, today he was not late to class, but let's say Sarath is late to class and I send him a Slack message and I say, Sarath, where are you? Would Sarath send me a list of 6 into 10 to the power 3 numbers? This is where I am. It would be complete, right? That if you really want to know where Sarath is, you need to know 6 into 10 to the power 23 numbers. Otherwise, something is missing. But Sarath won't do that, right? What would Sarath tell me? What would you tell me?
The approximate. So
how many things would you tell me? You tell me maybe one or two things, but you tell me I am 100 meters away from the chemistry building and I'm moving at the speed of light. So I can really get to your class, right? So two numbers kind of suffice, right? So the point I'm trying to make here is, even though matter is made up of a huge number of atoms, and what are we forgetting here? Is matter only made up of atoms? We can go deeper, right? We have electrons. And we have to go even deeper. Someone said Schrodinger equation, we have to think about electrons and their wave function. I think, right? You actually need even more information, right? It's more than this. But in reality, a handful, and this is where you start seeing my terrible handwriting, handful of variables suffice or are sufficient to describe matter. And here comes a key technical word, at equilibrium. Okay? This is very important. Why? Because let's go back to Sarath's example. Sarath told me that, okay, he's not going to tell me the coordinates of all 6 into 23 variables. He will just tell me where he is and which speed he's coming towards me with, right? But let's say Anjali got into a fight with Sarath, right? And she's like trying to punch him or something like that. Then maybe I need to know who is pulling Sarath in some other direction, right? So in that situation, Sarath is not in equilibrium. So anytime you're out of equilibrium, the number of variables start to increase. You have to figure out more things that are going on. They will rarely get to a full all-atom description of everything. But at equilibrium, and we will spend a lot of time really getting comfortable with what does equilibrium mean, where does it come from. But this as a concept should be kind of obvious to all of us, right? That when you have matter at equilibrium, you can get away with as few variables as you can. And a simple example, when I'm jumping like this and this, you need to use more variables to describe me, as opposed to when I'm sitting down calmly, right? The number of variables has goes down, right? So you can already see that when some change is going on actively, you probably need to have more variables, right? So the agenda for our 684 course really is 2 points. These are the only 2 points we are going to try to understand. Actually, only 1 point. I will first write down both and I'll tell you which one we are going to think about. First question that we ask is, why does equilibrium exist? What is equilibrium? What do we mean by it? How do we characterize it? How do we tell that something is at equilibrium? What does it even mean to say something like that? We will spend a good amount of time thinking about that, but what we will spend up more time thinking about is, once you know that something is in equilibrium, which variables do we need to describe equilibrium given experimental conditions? I will explain to you in just a moment what I mean by this. And this is why thermodynamics actually becomes super important for people doing experiments. They often don't appreciate it, but it's even more important in StatMech. StatMech is very easy, right? We all love S is equal to K log W. It's written on Boltzmann's grave. Has anyone seen that photo? Who has seen it? Raise your hand. Has anyone seen his grave? If you go to Vienna, you have to check out the grave. When I went there, that's the first thing I did. I came out and went and asked, how do I get to the cemetery? I go to the cemetery, there is his grave with S is equal to K log W next to the grave of Mozart and Beethoven and things like that. So what do I mean by this? What do I mean by given experimental conditions? Let's consider this cup of coffee, right? And I want to describe if this cup of coffee is at equilibrium, what variables do you need to describe it? Temperature, what else? Huh? Pressure, what else? You can't do pressure and volume at the same time. Go ahead.
External temperature.
We will get to that, but that's the same as temperature. Number, how much? So volume sounds like number, but it's not quite the same, right? You need to say how many moles of coffee are there. So number, pressure, temperature. Who said volume? Okay. Now, instead of that, I said pressure because it is in constant contact with the atmosphere. If I covered this, then you don't care about pressure. You want to know how much is the volume of this coffee, right? You don't buy a bottle of juice by figuring out, give me orange juice at this much pressure, right? You say, give me orange juice at this much volume because it's a closed container. You know what that is, right? So if you're doing an experiment in an open beaker versus an experiment in a closed furnace, the variables that you will use to describe it become different. And right now you can kind of see why it should be number volume temperature or number pressure temperature, but you look at it very carefully. My wife, who is a geologist here, she studies volcanoes. And sometimes volcanoes, when they explode, the best variables to describe them are things like enthalpy and volume and entropy. So it's highly non-trivial, but that's what works there. You know? So these are the two things we are going to understand slowly and build intuition, and then also use a lot of math to make it really powerful for us to use for different settings. So if I had to define thermodynamics, if I wanted to do that, this is how I would define it. Thermodynamics is the study of change of energy into other forms. And even though there is no time in thermodynamics, so that's one of the variables that will never ever show up in this semester. There is no time. Everything that we are talking about is what will happen in the limit of infinite time. There is no time ever, even though you got dynamics in the name. But the dynamics really comes from change. Now, when we talk about change, we can think about change in two possible ways, right? We can think about change in the sense of if, meaning if a certain change will happen, right? You have a folded protein. Is it going to unfold or is it going to stay folded, right? You have the cat looking at the ice cube, right? Is the ice cube going to melt or is it going to stay frozen, right? That's one aspect of change. The other aspect of change is when is change going to happen, right? This is something we are not going to study in chemical thermodynamics. We cannot answer the question of when will change happen. In the advanced topics, at the very end of the semester, if I have some time remaining, I will show you how you can use something known as transition state theory to get a sense of when out of thermodynamics, but that's an approximation. All we will do here is to say if a change will happen or not. We are going to make no claims about when it is going to happen, okay? And now you might say, well, that sounds like a waste of my time. I want to be, so you might say at this point, So you are not going to tell me anything about atoms or molecules because you are just going to say that we will work with very few variables. Second, you are not going to tell me when is change going to happen. So what's the point of this course? Well, it sets you up for really basics, for not just basics, it gives you a lot of tools also, but I want to pinpoint what comes after this course. What comes after 684. So next semester, which is spring 2024, many of you will take Chem 687, which is statistical mechanics and chemistry. That tends to be equilibrium statistical mechanics. So that one also will not answer your question of when. It will give you a more molecular atomic scale perspective of things. Normally, I have taught that course 5 or 6 times now. Next semester, I'm not teaching, so most probably Gary Popoyan or something will be teaching, which is fantastic. And then every other year, that is this. So this Chem 687 is a course that almost all of you will take, but every other year in spring. So it was taught in 2023. It will be probably taught again in 2025. There is an advanced course on non-equilibrium statistical mechanics, non-equilibrium stat mech, that generally Chris Zarzinski teaches. And this is perfect for you guys because it won't be taught in next spring, right? And that's when you will be taking Chem 687. It's not good news for the undergrad because he cannot take it. What's your name again? Undergrad.
That's fine.
Yeah. So, but that's a great course if you really want to study, and that's where you will get the time and things like that, and that's more advanced. So, I think Maryland is the only place where you can study. I don't know of any other place, and I have spent time at many institutions where thermo and stat mech are done in this much detail. So, and I think and it will be useful to you irrespective of what type of science you do. So yeah, so next spring 2024, you will almost all take Chem 687, and this course tends to be theoretically very inclined, the advanced course. So if you're doing simulations or theory, then you might consider that one later. Okay. Any questions so far? We haven't done much, but any questions? So far I've just told you that our agenda is to understand what is equilibrium, why does it exist, and we have some sense of equilibrium. You know when you are in equilibrium. All of you have currently moved to a new city, except few of you. So you're not in equilibrium. Everything is screwed up. You're trying to figure out. Some point you will get a sense, right? We associate equilibrium with a sense of calm, right? Things are kind of relaxed. You're in a flow. Everything is going on. We'll make it very quantitative. So what I want to do next is to give you some intuition into this comment that most of you or all of you nodded your heads at when I said, by using Sarath as an example, that at equilibrium, a handful of variables are sufficient to describe matter. Okay, so let's try to develop some intuition for this. Why is this true? Let's call this, it's not an equation, but I will still call it an equation, number 1. Okay, why is 1 true? And I will give you 2 reasonings, 2 ways of thinking about it, okay, as to why it might be true. So the first one says that anytime I'm observing something, I'm not observing it. Who here is working with Wendell Hill? You are working with it. So Wendell Hill, who is the chemical physics director, he does experiments where the time scale is attosecond. That's 10 to the power minus 18 seconds. But when I observe you, that's not my observation interval, unless you are in Wendell Hill's lab, right? Then yeah, you want to observe it over attosecond. Actually, I don't know what attosecond really means, right? Because uncertainty relation and things like that, so it becomes confusing. But when I observe Sarath or anyone else or this coffee, I observe it over a significant amount of time. What does that mean? That's kind of hard to quantify how much. But what is the least amount of time you can observe a cup of coffee? That depends on how quickly your eyebrows, eyelid flips and something like that. Maybe 10 times a second, right? Something like 0.1 second. Let's call it, I don't know, 100 milliseconds, something like that, right? Something like 10 milliseconds. There is no way you can tell me that just through your eyes, you can observe this coffee for 1 microsecond. That's out of the question, right? It's not going to happen. So if you're observing this coffee for 1 millisecond or longer, what are the atoms doing in that period? Are they in just one place? They probably move a lot, right? What is the frequency with which a hydrogen bond, a hydrogen atom oscillates? Anyone knows the number? In other words, I'm asking you, if you have a hydrogen bond, a hydrogen atom connected to another hydrogen atom, you know it is moving like this, right? So how many times in a second does it move? Who here has taken undergrad quantum mechanics? Come on then, Anjali, tell me. It's 10 to the power 15. It's a femtosecond. That's the typical number. In 1 second, a hydrogen bond will move 10 to the power 15 times, right? So if you're thinking about millisecond, most things have probably moved 10 to the power 12 times. They have moved a lot. So the point in reasoning one is, anytime you're observing matter, you're observing atoms over what might seem to you as a very small amount of time. What is a millisecond? Nothing, right? But from the perspective of that atom, it's an enormous amount of time that you have observed it, right? So anytime we observe matter, we do it over a long period of time. Again, long period of time is all relative. If you are an archaeologist who is interested in dinosaurs, then million years is probably not long enough for you, right? So if you're observing it over a long period of time, and let's say we have a box like this, and then in this box, we are seeing atoms moving around. So the idea is that we observe it long enough that in a general condition, the atom that was at the top of this coffee glass would have probably made quite a few trips to the bottom and come up, right? There is no point in saying atom number 1 is here and atom number 8 is here, right? That motion is averaged out. If you observed it for a picosecond, maybe it makes sense to talk about where the atoms are, right? And this plays out in everything. For example, we all have memories, right? We remember things. We often remember things. Maybe one day we will be 100 years old and we'll probably carry a memory from when we were 2 years old, right? So we have a memory which can last for 100 years. Do you know how long does a protein last in the human brain? What is the average life of a protein? It's way less than 100 years. It's something like a few hours. And yet memory persists for 100 years. Isn't that crazy? Just think about it. So yeah, so how actually memory is preserved in the brain is still kind of complicated. It's not clear because the protein it's no longer the same protein. Every few hours it's a different protein. So how is memory carried? Maybe there is some emergent structure, right? That structure is preserved. Anyway, so anytime we observe matter, things are moving all over the place and the motion averages out. So here I drew this red line which is moving all over the place. And let's say you started here at t is equal to 1 and you are over here at t is equal to 10. If you go to t is equal to 100, maybe you don't know where you're going to be. You could be anywhere in the box with any probability, right? So you just average out. So which means that there is no point in talking about, if things are just going to average about, why do you want to talk about them, right? Why didn't you want to talk about their actual values as a function of time? All you can say is to talk about some average value, right? So if you have such particles in a box, if this coffee cup is actually covered in such a way that I cannot compress this box, no energy can go inside it, and nothing can leak outside the box, okay? In this case, so if I have n particles in a box of volume V with total energy E. Okay. So if I have a box and if this, and I'm going to turn page in just a moment. Everyone good? Can I turn? Okay. And if this box is isolated, then at equilibrium, NVE are sufficient to describe this system. So I'm not proving this yet. I will get to it in maybe next class, but just giving you a sense, right? So the box could, the N could be Avogadro's number. And if you really wanted to be careful, you had to write down all 6 multiplied by 10 to the power 3 numbers. But what I'm saying is only 3 are sufficient. That's a huge reduction, right? Going from 6 into 10 to the power 23 to 3, that's kind of crazy. It's a huge, huge reduction. And why is this reduction justified? Because our observation interval is very, very long. It just does not matter. Okay, so this is one way of just giving you reasoning. The other way, it's very hand wavy, but the other way is a bit more precise. And we will gradually keep getting more and more rigorous in this course. The second way of reasoning, and here you will have to pay attention or it can become a bit confusing. I'm going to do a thought experiment, right? Especially since all of you are Einstein fans with E is equal to mc square. Einstein used to, he's the one who really popularized, right? The thought experiment idea. Anyone knows what it's called in German? Gedanken? No one has heard that word. So Einstein did not do any experiments, right? He won the Nobel Prize, but everything he did was just like sitting and imagining what if light is moving in a certain speed in a car and things like that, right? They were all thought experiments. So we are going to do a thought experiment. We are going to imagine a box. Okay. In this box, we are going to put a boundary in the middle. This boundary in the middle, what is it? It is a rigid piston with no heat or mass transfer. So the piston, it's just a tight thing in the middle of a box which cannot move to the left or right. No heat can go through it, no energy can go through it, no mass can go through it, okay? And the full thing, this whole thing is isolated or insulated, whatever you want to call it. So now let's call the thing on the left as system A and the thing on the right as system B. So system A is basically oblivious. Yeah, go ahead.
Is the pressure same for the two parts? Like
If what is same?
pressure.
Oh, we haven't gotten to pressure yet. Hold on. Patient. We'll get to pressure in just a bit. So these are two boxes which for all practical purposes are oblivious of what's going on in the other side, right? They have no idea. There is no way for them to communicate. Okay, we'll get to pressure in just a bit. So in this case, from what I wrote above, you would need N. You need to characterize how many atoms do you have in system A. Let's call it Na, okay? You need to characterize what is the volume of system A. Let's call it Va. And you need to characterize what is the energy of system A. Let's call it Ea, okay? Same for system B. Here you need to say Nb, Vb, and Eb. So how many numbers in total? 6 numbers, right? Now let's do our thought experiment. I mean, we have just set it up. Now we will do the actual experiment. And that's what pressure will matter. We will do 3 experiments, okay? In the first one, let the piston move left or right. So originally we had it fixed. We had just kept it where it was. Now we let it move left or right, okay? In the second one, allow heat to move through the piston. In the third one, allow mass to move through the piston. What will be the effect of this experiment? What will be the effect of experiment number 1? Correct?
N changes. Or,
No,
sorry,
1,
volume
experiment
changes.
1, the volume changes. Until when? Will the piston just move to the extreme right and stay over here? You're correct, volume changes.
Yeah.
But till when?
Equilibrium.
What type of equilibrium? What does it mean? Until the pressure becomes equal, right? You have a piston. Why does the piston want to move? Because you are punching it from the left side. The other atoms are punching it from the right side. And whoever is punching harder on an average will move it in that direction, right? It's like a tug of war. So this first experiment will change volume until equilibrium is established. But this equilibrium has a name now. This is called mechanical equilibrium, right? Things won't move anymore until mechanical equilibrium. And mechanical equilibrium will be characterized by the pressure of A becoming the same as pressure of B. Okay, how about the second experiment? So now you have allowed the piston to move in the first one. It can move left or right, okay, and it stops at some point, okay, when the pressure becomes equal. Now you are allowing heat to go through the system. When will this process stop? Will it ever stop? When TA is equal to TB, and this is called thermal equilibrium. Does thermal equilibrium mean that heat is no longer going from side A to side B? No. It's still going, but on an average, it's not going, right? It's on an average, it's balanced out now, right? That's the idea. How about the third one? When you allow mass to move through the piston, that leads to chemical equilibrium, right? And chemical potential has to become equal. So this will happen until mu A is equal to mu B, or chemical equilibrium. So these are the three types of equilibrium we talk about in this course. There is no reason why these are the only equilibriums that can exist in nature. Can someone think about a fourth type of equilibrium that might matter? How about information equilibrium? Right? That's how electrical engineering, a lot of information theory is based on. You can model information as something like this, right? I'm giving you ideas, you are giving me ideas, and you can balance it as a chemical potential of information, things like that, right? You can generalize all this. You can generalize it in many, many different ways. So what was the effect of, so what did we do in this thought experiment? We had an internal constraint and we removed it, right? Things can move left or right. So the point I'm trying to make here is, let's think about the number of variables we now need, the number of independent variables we now need to describe the system. This independent word is very, very crucial. So earlier we needed 6, right? Now how many do we need? Why 12?
That's PA,
Good point, but PA is equal to PB. So just P. And VA is equal to V. TA is equal to TB. So this is interesting, right? So imagine that you can't say anything about VA and VB at equilibrium because that's going to be moving back and forth, right? So it's like, so does anyone here like camping? Do you like camping? Imagine you have put up a tent and there's a lot of wind going on, right? So it does not mean, and at some point you reach equilibrium between the wind that is blowing outside and I don't know, you're reading a book and contemplating life inside, whatever, right? That does not mean the volume of the tent is constant. It is fluctuating, right? But the average pressure is same. So what happens after this thought experiment is that initially, while you needed NA, NB, VA, VB, EA, EB, once you attain equilibrium, you are no longer thinking in those variables. You are thinking in pressure, temperature, and chemical potential. So instead of 6, now you need 3. Okay, so suddenly we have jumped up a level of abstraction. You'll be like, wait, why don't I need to know N and E and B? You don't. The system is characterized fully by these 3. If you know the values of these 3, you know it's an equilibrium state. Any questions? Some of the material that I cover, you will go back and be like, I don't buy that. That's confusing. So ask me on Slack, okay? And I really encourage to ask in general on Slack, not by sending me direct message, because we can have a discussion that way. So we just saw 3 types of equilibrium: mechanical equilibrium, chemical equilibrium, and thermal equilibrium. This is a good point for me to tell you about the 3 types of fun. So when I was in grad school, when I was a young person like you all, I used to do a lot of rock climbing. And this is where you lived in LA, right? So I used to go climb in Joshua Tree and, Santa Monica and all those places. So this comes from the climbing community, that there are 3 types of fun. There's type 1, type 2, type 3. Type 1 fun is fun when you're doing it. Okay, like having a barbecue or having drinks, or just going out for a nice hike with your friends where everything is great, the weather is awesome, no problem, right? So type 1 is, don't take this down. This is not going to be on homework or exam. Fun when you are doing it. Type 2 fun is fun in retrospect. It sucks when you're doing it, okay? You don't like it. It's like, again, from the hiking side, normally it happens when it's just snowed. You're from Wisconsin, right? So you know it. When you're walking in a lot of snow and it sucks when you're walking in snow. But when you get back into a nice warm room, you're like, oh, it was nice walking in snow, right? It was great. The view was fantastic, right? So fun in retrospect. Type 3 fun is not fun, ever. You did it, you think about it, you still hate it, okay? Can anyone think example of type 3 fun? Hopefully not your PhD. Okay, so this course is going to be somewhere around type 2.1 fun on an average. For some of you, it will go to 1.5. Some of you, it will leer dangerously close to 3. Okay, and I will check every once in a while. What fun are these? So this is important because I will do a mid-course evaluation where I will ask for more qualitative feedback, but every once in a while, I will just send like an anonymous quick quiz where I will ask you to rank what fun is it currently, okay? So that's why this is important that we are on the same page. So type 1 is fun when you're doing it. If everyone says type 1 fun, that means the course is too easy. You're all having too good of a time. I need to ramp it up. If everyone says it's type 3, that means I really don't know what I'm doing here, right? So we want it to be somewhere in the middle. Okay. So getting back to the 3 types of equilibrium, what did we just show with this thing, with our thought experiment? We did 2 thought experiments. One is that we thought about observing matter for a long enough period of time, and the other one was removing internal constraints, right? And the effect of both of them was the number of independent variables that we needed went down. So like in this case, what's your name in the orange shirt? Steven. Steven said you need PA and PB. He's correct. But they are no longer independent, right? If you know PA, you know PB. They are the same thing, right? That's the point. So the number of independent variables went down. So the point to keep in mind is that removing internal constraints from a system or observing a system long enough both of these the system reaches a very special state that requires very few variables to describe it. This is the state of equilibrium. Okay. Is this clear mostly? It's a bit abstract, you know, thermodynamics feels a little bit like philosophy in the beginning. There will be lots of math. Yeah, please. What's your name? Okay. Oh, that's me trying to be nothing. It's really nothing. I was trying to say that leads to. It's a special symbol. Yeah. Now we are ready to talk about something very, very concrete, which is, if you read Callan's book, he does not go does not start with postulates. What is the purest of sciences? Math, probably, right? It's or number theory, something like that, right? Even there you have postulates. Real numbers exist. How do we know real numbers exist? We just start with that real numbers exist. And actually you can keep bringing it more and more and more and more basic. The most basic postulate is that integers exist. I think it's known as Dedekind's postulate or something like that. You can't prove it. You have to start from there. So at some point you have to stop. And you build up from that and you check for self-consistencies, right? The postulate should allow you to make some predictions and you should be able to verify those predictions. Otherwise, I can make any postulate, right? I hereby postulate that all of you are to give me $1,000 tomorrow. Should you do that? No, because that's crap postulate, right? It doesn't mean anything. Right? So the first postulate in Callan, and I will write down this statement and then talk about it, is that, oh wait, it's 12:15, I'm done. We will start with Callan's postulate next time. So get hold of Callan. Again, you can buy it online or you can share it, whichever way. I have no comments on that. So see you next, see you on Thursday.